开始吗？好，有开始。
还有
真的。
我也会紧张啊，因为我没有用，我上一次用英文上课是我在台大念博班的时候，然后刚好那门课是暑修，很多人上去补，大概200-300个人，底下就会有从台大各系、医学系想要先超修的，然后物理系、化学系，然后重点就是会有国际学生，然后那国际学生底下就坐了一对黑人情侣，然后那个黑人就看起来呢感觉很 tough， 他就说主教可以用英文讲一遍嘛。然后就当场错到，然后就讲半节课之后呢，我看其他人好像傻掉了，然后下一节又改成中文，因为他并没有说这门课如果要英文授课的话，一开始要讲清楚啊。然后我自己开多元选修讲比较趣味的实验是可以用英文的，但是你知道去讲这种比较专业的高中课程，有它的根本性难度，因为它不是聊天，知道吗？聊天的话就是要不要上厕所，要不要吃饭什么的。所以呢，那我们今天就来试看看，好吗？那我们现在就要把那个 mode 切换一下了。你板书好，板书也用英文。Let's get started. Okay, as you can see, the topic is kinetic molecular theory of gases. In Chinese, it's called 气体动力论. Kinetic molecular theory of gases. Let's try to imagine. Since a balloon is pretty, the weight is not that high, but the pressure inside it is pretty big. So the pressure for the gases cannot be explained by its weight. It should be explained by its collision. So the reason why we want to talk about the kinetic molecular theory of gases is that we want to find out what is the underlying reason to generate the pressure inside the container. Okay, so first let me prepare a cube, 3 dimension. It will be easier for us to discuss the container, so I've prepared as a cube, so the height and the length and the weight should be equal to each other, and that will be easier for us to talk. I need to make a claim. The claim is that the molecule inside this container, you get a huge amount. There are thousands of molecules inside this container, so it's now flying around inside it, and you don't know which direction it would be more preferred. In fact, you cannot say that it will be more preferred than preferred to move along X direction or the Y direction or the Z direction. Why would it be any different? Well, that doesn't make any sense. It's not flying randomly inside this container. And there's one thing that you should know. The velocity of all the molecules are different from each other, but finally we will want to find an average kinetic energy to represent one of them. Okay, now we want to specifically discuss the pressure of a wall on the right-hand side. And let me redraw it again. Because there are lots of molecules, so I'll just number them as number 1 molecule, number 2 molecule, and number n molecule. And I'll use a simple I to denote one of them. And now they are ready to strike the wall on the right-hand side container. let me do some simple assumption that this is ideal gas. Ideal gas, what is ideal gas? They don't really interact with each other. So you can forget about the van der Waals forces existent among them, okay? So if there's any interaction between those molecules, that would be the collision. So for the elastic collision, that means it won't make any kinetic energy loss when they do the collision. Okay, so when the molecule number I is ready to strike the wall on the right hand side, it will bounce backwards, and there will be no loss of kinetic energy. So it will follow the reflection law. The incident angle and the reflection angle will be equal to each other. Since it's now doing the elastic collision, we don't need to care about the velocity in the y component. We only need to care about the x component. So now I want to find out the change of velocity. The change of velocity is not during the elastic collision. So along y-axis there will be no force acting on the molecules. There will only be a normal force. So you will only see the change in the normal direction. You will only see the change in x direction. So we would derive the change of velocity can be written as 2 times v. Vx means the velocity in x direction. So now I want to keep going. I want to derive the change in momentum. Why? Because I want to talk about the pressure. If I want to talk about the pressure, I need to have the force. If I want to have the force, I need to first derive the change in momentum, because the change in momentum per delta t is the force, right? So now I have the force a little bit nervous. The change of momentum 就是动量的意思. So I want to get the change of momentum. The change of momentum delta p, I means the random number, maybe number 1, number 2, number 3, is equal to mass times the change of velocity, and that will be 2 and vx. Okay, now I can go deep. I can go further. If I have the change in momentum, so I will successfully derive the average force of a single molecule. What is force? Force is very simple. Force is the change in momentum, the delta p per time. So you can put the 2 mvx on the top, and the bottom will be the delta t. So this is the hardest part to realize the kinetic molecular theory of gases, because it's not really not that easy to realize why would I put the delta t as 2L divided by the velocity in the x direction. This is the hardest part. Almost seldom of us can really understand the choice of delta t. So let me draw another axis to help you understand it. I'll draw the y-axis versus x-axis. Since number I molecule is now striking the wall of the container, and it will bounce and it will do the elastic collision. So if you just pay attention to this x component, the velocity in the x direction, once when you do the elastic collision, it will bounce backwards with the same size of speed and move in the opposite direction until it hit the other side of the wall, and then it will bounce back again. So next time when you travel back to the original right-hand side wall, you would take the time for 2L divided by the Vx. Okay, so if the y-axis is the force provided by the molecule, and the x-axis is time t, and we have this function. Let me tell you something. This is the real time for a single molecule to interact with the container. But what I really care about is the traveling time when it travels back to the right-hand side wall of the container. This is the time when you hit the wall, and this is the end of the collision. And the next time when you do another collision, when you finish the next collision, the delta t right here is 2L divided by the velocity in the x direction. Some people might be confused. Why should I put the 2L over Vx right here? Because I should put a real time. I should put a real time like delta t naught. I should put the delta t on the bottom. So why should I choose the 2L over Vx? This is quite confusing. Let me tell you something. Maybe you are now charging your cell phone. You're charging your cell phone nearby the wall, and the output voltage is around 110. But we have, as we all know, that the power is AC current. It's AC current. It's not due to the oscillation. It oscillates like a sine function. But when you are charging your phone, we don't always get the maximum voltage. We don't always get the maximum voltage. And of course, we don't always get the zero voltage. However, you have a static value of the voltage, right? So the output voltage, okay, is, let me tell you the answer is Roomy square voltage. Okay, this is the same idea to realize why should I choose this item as our delta t. Because this is the gap. There will be a time gap. There will be a time gap. Next time when the molecule hit the wall. But during that time gap, try to imagine your container is a balloon. Will your balloon collapse during the time gap? Actually, your balloon will remain in the same shape, and the pressure inside is a static value. So even though there's a time gap, they only happen one collision with a very short time. But during the time gap, the pressure inside this container is still the same. It still will be a static value. So in order to derive the average force of a single molecule, and this changeable momentum should be divided by the time gap. Okay, the time for the molecule to travel back and forth inside this container. Okay, there's another way to accept this delta t. How to do that? Because I want to discuss all the molecules of the contribution from all the molecules. So I'm going to just simply discuss the force from a single molecule. I want the force, I want the contribution from all the molecules. So I should wait till all the particles collide to do a collision with wall on the right hand side. So you can imagine this delta t as a time that you should wait. The time you should wait till all the molecules do the collision. Okay, I'll draw you a picture to understand. This is the wall on the right hand side. When the number one particle hit the wall, and for those particles, just right behind it will be the next one. And which one will be the latest is the nearby particle. Just right near it. When the particle 1 is ready to strike the wall and the nearby particle is moving in opposite direction, and for the other particles will be earlier than the number n particle. You will now travel in the opposite direction, and next time when they travel back to the right-hand side wall, it takes time. Delta T is equal to 2L divided by the Vx. Because I want the contribution from all the molecules, so I should wait. If you choose to use the real time for the collision, and during such a short time, it is impossible for all the molecules to have interact with the wall of the container. So you should wait. You should wait till all the particles, all the molecule gases do the collision with the right side wall. Okay, I've done my best to help you accept the delta T as this item. When I was a student around 17 years old, after the class, I go to ask my teacher, why should we put the delta T as this form? Why can I use delta T not? And it taught me that I don't understand. Okay, so I hope you can understand this concept. Let me go further. Let's delete the 2, and the force can be written as m times Vx squared divided by the length. Okay, now we are ready to do the next step. This is the force, average force of a single molecule, but I want all the contribution from all the molecules. So the next step is you add the forces all together. You sum the forces, okay? In order to sum the forces, I use the symbol sigma Fi, and this is mass is a constant, the L is a constant. I put it right in front. There are thousands of molecules inside this container, so the Vx means the x component of a random gas. Now I need to sum all of them, so I can write it as v1x squared plus v2x squared. Let's keep going. V and x squared. This is the sum of v squared, the x component of all molecules. This would like an average value. If I could put an n down below, and let's now divide the x, and let's now divide the whole item by m. Since you cannot do this without any reason, so I should put it back right on the top. Can you accept this? So look at this whole item. I first square them all, and then I average them all. So this should be an average value of the Vx squared of all the molecules. So I can make it simple. I can make it simple like this. Vx squared, and this is beautiful because I need to put a bar right over the top of here, and this means average value. This is the average value of Vx squared, and the Vx is a sum. It's a sum of all the molecules, like V1x squared plus V2x squared, and keep going, plus Vnx squared. This is the average value of Vx squared of all the molecules. So do you feel excited? Because now I have already derived the relationship between the microscopic quantity to macroscopic quantity. The macroscopic quantity is like the force, the pressure. 巨观的物理量像是你的压力啊，像微观的 the microscopic quantity like the velocity of a molecule. 像是我们现在就有这个 x 轴，分子在 x 轴方向的速度。 and I find out the relationship between the microscopic quantity and the macroscopic quantity. This is quite amazing because if I want to realize the pressure inside this classroom, and all of you are the molecules, I just need to capture one of you and ask you, what is your kinetic energy? They say, my kinetic energy is 3 joules. Okay, now I could get the pressure of your class. That is amazing. Okay, let me clean it. But in this part, the main destination is I want to derive the pressure P. The pressure P. What is pressure P? Pressure P is the force. Per area. Force per area. The force now should be considered as the sum of all the molecules, the contribution of all the molecules. I try to make it look similar. I put a sigma I right here. And the sigma Fi is right here. So I will capture this item and replace the simple item, and can be written as A, L, and capital M times mass, and the Vx squared, the average value of the Vx squared. But I want to find an equation. I want to make it more complete. If I could only have the x component of the velocity, it is not complete. It is not complete. I want to change the x component to the real velocity. So you can imagine if this is your particle, and has x component along x-axis and the y component and the z component. And you square them all and add them together, you will have the real velocity, and you square it is equal to vx squared plus vy squared and plus vz squared. This is for single molecule. And now listen carefully. I can write this as v1 squared, which is equal to v1x squared, v1y squared, and v1z squared. And so as the v2 squared is equal to v2x squared, v2y squared plus v2z squared. So if this equation is true, and it would be also true if I put a bar right over here. Okay, I will add all the molecules. That will also be true. 这边担心你们有点听不懂，意思就是说啊，如果我把这个 v1 平方 v1 squared is equal to v1x squared plus v1y squared plus v1z squared, and so as v2 squared is equal to v2x squared. Let's go on and on. To the number n molecule. Okay, now you can add all of them. This is sum of v squared, and you divide them by the capital N, and you will get the average value. Okay, because I want to make it quick, so I say the average value of v squared from all the molecules can be written as it. And now, listen carefully. The three items should be equal to each other. Like this. The vx squared is equal to vy squared, and is equal to vz squared. Because let me make it plain, because inside this container, all the molecules are now flying randomly. It doesn't have any tendency to move specifically move along the x-axis or the y-axis. So they got the same percentage to move along the three axes. So why would I be any different? I don't have to be any different. So that is why the contribution toward x-axis and y-axis and z-axis is equal to each other. So I can fairly write this vx squared, the average of the vx squared, as 1/3 the average value of v squared. Okay? This area times the width because I assume that this container is a cube. So the height, the width, and the length, they are the same, all the same. So when the area, you multiply the area by the length L, is the volume. It's the volume. So I can write the L as the volume. Volume, TD, volume, TD. Keep going, and times the mass. I put a 3 down below, v squared, I put it all right at the top here. Okay, now we get this equation that can relate the microscopic quantity to macroscopic quantity, and that is your pressure can be expressed by the velocity, and the velocity is information from a single molecule, and the pressure is information about the whole container contributed by the whole molecules, and this is a surprise, and this is amazing. Okay? 也就是我们现在可以成功的用一个分子的速度，分子的平均速度，你就可以得到这个巨观的物理量 macroscopic quantity. Okay, let me define another symbol for you. This is the average value of v squared, and the v squared is the contribution from all the molecules. You add them all, like the v1 squared plus v2 squared plus v3 squared. You square them all, and you average them all by divided by the capital M. Okay. And the average value of the v squared, if you try to put a square root, the square root of this O item, the square root of this O item will be defined as the root mean square velocity. Root mean square velocity. Okay, this is the new symbol. 这个在中文上叫做方均根数律，或讲这个均方根数律。这个 root 就是跟 root mean square。那你把所有数律的平方相加，再取平均值派根号。And the square root of the average value of the v square, and that will be defined as VRMS. So now I have complete the proof that the pressure can be written as 3 times the volume, the capital M, times mass, and times VRMS, the root mean square velocity. There's one more thing I need to tell you that for ideal gas, we all know that the PV is equal to nRT and capital N times K times T, right? So, let me explain this for you. The PV is now equal to 1/3 N times M and times VRMS squared. It is also equal to nRT and nKT. And K means the Boltzmann constant. Boltzmann constant 1.38 times 10 to the power of minus 23rd. Okay. Listen carefully. Does it look familiar? The m times v squared, does it look familiar? It's just like kinetic energy. So I can put a 1/2 in front of it, like this. I put a 1/2 1/2 in front of it. Wow, that's interesting because this is the average value of the kinetic energy from a single molecule. And you put a 2 right here on the top, so that won't make any change. So I can rewrite this as 2/3 N times K. So in addition to PV is equal to nRT and capital NKT, now you have a new equation that it can be written as 2/3 NK. And the K means the average value of a kinetic energy from a single molecule. Okay. So that means 你现在可以用一个分子的动能，然后你就可以得到很巨观的这个压力去乘上这个体积。The pressure times the volume is equal to 2/3 NK. K 就是你一个分子的平均动能。所以我们就把这个 macroscopic quantity and microscopic quantity 把它连接起来了。那如果你再把这个 2/3 NK and nRT NKT 稍微转一下的话，你就可以得到一个分子的平均动能。The average value of a kinetic energy can be written as 3/2 Boltzmann constant times the temperature. And this is also equal to 1/2 mv squared. 所以不仅是你用微观的动能可以得到一个巨观的压力跟体积，其实你可以反过来，你用这个巨观的温度 the macroscopic quantity， 然后呢 back to 了解一个分子的动能，所以这就是它有趣的地方。气体动力论呢，就是找到巨观物理量跟微观物理量之间的这个关系。我们可以把巨观的 PV 用这个2/3分 K 用分子的动能就可以得到。那再来就是也可以反过来用温度就可以得到一个分子。所以我们从前有说过什么叫温度啊？温度就是分子平均动能的表现。In Chinese. What is more interesting is they don't care about the types of gases, the helium, the nitrogen. 不是这分子的种类不是太重要。那如果你是单原子分子的话，不管是什么种类，你的这个 mass might be different from each other. Your mass might be different from each other. 但是呢，它们都可以用2/3 KT 来表示。你可能是单原子1号，你是单原子2号。Number 1 molecule, number 2 molecule, but you are all monatomic atom, and your kinetic energy can be all written as 2/3 KT. 你们的动能都可以写成2/3 KT. 如果你的这个质量比较大的话 ，your mass is now is huge, is more huge， 那你的速度就会动得慢一点，平均来说 ，OK 吗？好。这也算是被你们刺激到因为你们是武陵高中的学生，因为2030年要推双语国家，所以之后你会很常可能几年以后会看到学科老师用英文上，当然大部分老师是比较恐惧的，连我也是那昨天是想说如果连男女混校第一志愿